Some worlds vanish completely from the universe. We will uncover the secret histories of lost planets, from ancient myths to modern cosmic mysteries. You will learn exactly how entire worlds can disappear and what these celestial ghosts reveal about our own solar system's violent past. How could a planet astronomers once swore was real, like the phantom world Vulcan orbiting near the Sun, simply cease to exist? What catastrophic event might have shattered a fifth giant planet, flinging its pieces into the dark? By the end, you will see the night sky not as a static map, but as a graveyard of forgotten worlds and a stage for cosmic chaos. Does our solar system hold the ghostly fingerprints of planets that are no longer there? A lost planet is not merely one we have yet to find. It is a ghost in the machine of astronomy, a world that once held a place in our charts, our cultures, or our equations, only to vanish from our certainty. These are the celestial bodies that were hypothesized to explain the wobble of a star or the strange drift of a neighbor's orbit. They are the worlds spoken of in ancient myths, described with conviction but leaving no physical trace for our telescopes. They even include promising dots of light around distant stars that newer, better data simply could not confirm. This broad definition forces us to confront a humbling truth. Our map of the cosmos is not a static document. It is a living, changing story, and lost planets are the paragraphs we once believed were true but have since had to cross out. To understand them is to step into a shadowy realm where scientific confidence meets cosmic mystery. How does an entire world become a footnote, or worse, a forgotten era? The answer lies in the very methods we use to explore the heavens. For centuries, astronomers relied on prediction and painstaking observation, connecting dots of light in the sky. Sometimes those dots seemed to tell a story that demanded a new character, a hidden planet pulling strings from the darkness. But what happens when that character never shows up for its grand entrance? That confidence was soon put to the ultimate test. In the mid-19th century, the brilliant French mathematician Urbain Le Verrier noticed something deeply unsettling about the planet Mercury. Its orbit was not a perfect, repeating ellipse. Instead, the point where it came closest to the Sun, its perihelion, was slowly drifting or precessing over time. Newtonian physics could explain most of this drift, but not all of it. A tiny, stubborn fraction of the motion remained unaccounted for. Le Verrier, fresh from his triumphant prediction of Neptune's existence, applied the same logic. He declared that the only possible explanation was the gravitational pull of an unseen world, a small planet orbiting even closer to the Sun. He named this hypothetical world Vulcan. The announcement sent a wave of excitement through the astronomical community. Reputable observers across Europe and America trained their telescopes on the Sun, hoping to catch a glimpse of this elusive interloper during a solar eclipse or as a tiny black dot transiting the solar disk. And soon, reports began to trickle in. A country doctor in France claimed to have seen a round spot moving across the Sun. A respected astronomer in the United States reported a similar observation. For a time, Vulcan was considered real, its existence cemented in scientific journals and textbooks. Yet, the sightings were always fleeting and impossible to confirm. The evidence was like smoke, visible one moment and gone the next. The ghost of Vulcan haunted astronomy for decades, a planet built on impeccable mathematics, but existing only in the space between hope and observation. Its ultimate demise did not come from a better telescope, but from a revolutionary new idea. A young physicist named Albert Einstein developed his theory of general relativity, which reimagined gravity itself. He proposed that massive objects like the Sun warp the fabric of space and time around them. Mercury, orbiting so close to the Sun, was moving through this profoundly curved space. Einstein calculated the exact amount of Mercury's orbital drift caused by this curvature. His result matched the anomalous precession perfectly. The mystery was solved not by adding a new planet, but by rewriting the rules of the cosmos. Vulcan was no longer needed. Its story stands as a permanent monument to scientific humility. It shows us that even the most logical deductions, backed by the greatest minds of an era, can be a beautiful, compelling error. The ghost of Vulcan teaches us that sometimes to find the answer, we must not look for new worlds, but question the very universe we think we know. But the human mind was telling stories of lost worlds long before we had the mathematics to predict them. Look up at the night sky, and you are also looking into an ancient storybook filled with celestial dramas of creation and destruction. The Babylonians told of the goddess Tiamat, a primordial being of salt water who engaged in a violent cosmic war. In some modern interpretations, this myth is read as an allegory for a planetary catastrophe. A great world shattered in the early solar system to form the asteroid belt and the Earth itself. Then there is the Greek legend of Phaeton, the reckless son of the sun god Helios. He begged to drive his father's fiery chariot across the sky for a single day but lost control, scorching the earth and forcing Zeus to strike him down with a thunderbolt. Later thinkers would wonder if this story, too, was a distorted memory of a planetary disaster, a world that flew too close to the sun and was obliterated. These myths were not science, of course. They were humanity's first attempts to impose order on a chaotic cosmos, to explain why a star might suddenly appear where none was before, or why the planets wandered on their strange paths. They reveal a deep, instinctual understanding that the sky is not a permanent, unchanging vault. It is a place of immense power and occasional violence. That narrative thread, connecting celestial events to stories of loss and transformation, is the very same thread that would later lead astronomers to search for Vulcan. It is the foundation upon which our entire concept of a lost planet is built. What if the myths were not just stories, but a different kind of map, one charting not the positions of worlds, but the profound human need to find meaning in the void? The same human instinct that crafted myths of celestial destruction also sought mathematical order in the heavens. That search for a pattern led directly to one of the most intriguing and ultimately flawed ideas in the history of astronomy, the Titius-Bode Law. It began not as a grand theory, but as a simple numerical curiosity. In the 1770s, astronomers Johann Titius and Johann Bode noted a strange sequence. If you start with 0, then add 4, and then double the number each time, you get a series that seemed to mirror the distances of the planets from the Sun. Mercury fit at 4, Venus at 7, Earth at 10, Mars at 16, but then there was a gap at 28. Jupiter followed perfectly at 52 and Saturn at 100. That empty space at 28 was a glaring hole in the pattern, a silent prediction screaming for a planet to be found between Mars and Jupiter. For decades, this was just a numerical coincidence. But when William Herschel discovered Uranus in 1781, its orbit fit the law's next predicted distance almost perfectly. Suddenly, the Titius-Bode Law was transformed from a curiosity into a potential key to the solar system's architecture. The hunt for the missing world began in earnest. Astronomers formed a dedicated group, the Celestial Police, with the express mission of patrolling the gap and finding this phantom planet. They did not find a single world. Instead, on the first night of the 19th century, Giuseppe Piazzi found something entirely different, a small, moving point of light he initially named Ceres. Soon others were discovered: Pallas, Juno, Vesta. Instead of one planet, they had found a vast collection of fragments, the asteroid belt. The immediate, thrilling conclusion was that they had found the remains of the lost planet, shattered by some ancient cosmic collision. Many called it Phaeton, directly linking it to the Greek myth of the sun who flew too close to the sun. For a time, it seemed the mathematical ghost had led them to a real, tangible catastrophe. The pattern had worked, but as more asteroids were discovered, and as our understanding of gravity and solar system formation deepened, the Titius-Bode Law began to crumble. The discovery of Neptune, whose orbit did not fit the sequence at all, was a major blow. It became clear that the law was a fortunate coincidence, a pattern that worked for some planets but had no real physical basis. It was a beautiful dead end, yet its legacy is profound. This mathematical ghost, this elegant but incorrect rule, directly guided telescopes to the asteroid belt. It showed us that even our mistakes can lead to monumental discoveries. The search for a single lost world revealed instead a sprawling graveyard of cosmic rubble, a reminder that the space between planets is not empty, but filled with the whispers of what might have been. The romantic idea of a single shattered world, christened Phaeton, is a powerful story, but the truth of the asteroid belt is far stranger and more complex than a simple planetary explosion. If a full-sized planet once orbited between Mars and Jupiter, its destruction would have left behind a specific kind of evidence. We would expect the countless asteroids to be composed of similar rock, the shattered pieces of a single, cohesive body. Yet when we analyze them, we find a stunning diversity. Some asteroids are metallic, dense cores of iron and nickel. Others are stony, like the crust of a planet, while another class is rich in carbon and primitive, water-bearing minerals. This is not the uniform debris field of a single catastrophe. It is a collection of fundamentally different building blocks, each telling its own story. So what really happened in that vast space? The leading theory points not to a destructive end, but to a beginning that was never finished. In the early solar system, this region was a swirling disk of dust and gas, just like the areas where the planets successfully formed. But nearby, the immense gravitational pull of the growing planet Jupiter acted like a cosmic tyrant. Its powerful tides constantly stirred the protoplanetary material, preventing the small, rocky clumps from ever coalescing into a single, stable world. Jupiter's gravity either flung these infant planetesimals into the Sun, ejected them from the solar system entirely, or locked them into the chaotic, jostling orbits we see today. It was a factory of worlds that was shut down before production could truly begin. There is, however, another compelling layer to this story. While a full-sized Phaeton is unlikely, catastrophic collisions did occur on a smaller scale. We see families of asteroids that share nearly identical orbits and compositions, clear evidence that larger parent bodies were indeed smashed apart in monumental impacts. So the asteroid belt is not the grave of one lost planet, but a cosmic museum. It is a frozen snapshot of the solar system's violent youth, a place where some worlds were stillborn due to a giant's influence, and others were broken apart after they formed. The phantom planet Phaeton, then, is a beautiful idea born from our desire for a neat and dramatic narrative. The reality is a messy, magnificent relic of creation and disruption, a ring of planetary embryos and fragments that never knew unity. What other secrets are locked within these drifting mountains of rock and metal, waiting to rewrite our understanding of the solar system's turbulent birth? The asteroid belt shows us a story of creation interrupted, but to find a truly epic tale of loss, we must travel outward to the realm of the giants. The outer solar system, with its 4 majestic gas planets, seems like a picture of stability, yet their serene orbits hide a violent secret. For decades, astronomers were puzzled by the peculiar arrangement of these worlds. Computer simulations of the solar system's formation consistently failed to reproduce the precise orbits we see today. The models suggested the planets should have ended up in very different positions, or that the entire system should have been torn apart. Something was missing from the equation, a dramatic event that reshaped the entire outer solar system in its youth. The most compelling solution to this cosmic puzzle is the fifth giant hypothesis. This theory proposes that our Sun originally had not 4 but 5 large gaseous planets. According to the models, this fifth giant, a world similar in size to Uranus or Neptune, was catastrophically ejected from the solar system in a gravitational slingshot event. Imagine the early solar system as a crowded billiards table, with these young, massive planets jostling for position in a dense disk of gas and debris. Their gravitational pulls tugged at one another, creating a chaotic dance. In one pivotal moment, the fifth giant passed too close to Jupiter, the solar system's gravitational titan. Jupiter's immense gravity acted like a cosmic catapult, flinging the smaller giant out of the solar system entirely, sending it on a one-way trip into the freezing darkness of interstellar space. This single, violent event perfectly explains the orbits we observe. The recoil from this ejection would have nudged Jupiter inward slightly while pushing Saturn, Uranus, and Neptune outward into their current positions. It also provides a clean explanation for the strange, scattered objects in the Kuiper belt, a distant ring of icy bodies beyond Neptune. Their orbits are exactly what you would expect from the gravitational shockwaves of a planet being violently expelled. This lost giant was never a small, rocky world like the hypothetical Phaeton. It was a fully formed colossus, a sibling to the planets we know, condemned to wander the galaxy alone. Its ghostly fingerprint is etched into the very architecture of our solar system, a permanent scar from a time of cosmic chaos. What would it be like to look up at a sky graced by 5 giant planets? We will never know, because that stability was bought with a price, the sacrifice of an entire world to the void. That wandering fifth giant was not the only possible casualty of the solar system's violent youth. Closer to home, the rocky inner planets bear their own scars from a mysterious era of fire and bombardment. The surfaces of the Moon, Mercury, and Mars are pockmarked with vast craters, evidence of a cataclysmic period known as the Late Heavy Bombardment. For hundreds of millions of years, it seemed, a relentless storm of asteroids and comets rained down on the inner solar system. But where did this celestial artillery come from, and what triggered it? One compelling, though controversial, answer involves another lost world, a phantom known as Planet V. Imagine a fifth rocky planet, not a gas giant, orbiting in the gap between Mars and the asteroid belt. This world, slightly smaller than Mars, would have been a neighbor to the red planet in a much more crowded inner solar system. For a time, its orbit might have been stable. But according to the Planet V hypothesis, the gravitational chaos unleashed by the ejection of the fifth giant in the outer solar system sent ripples inward. These ripples destabilized Planet V's delicate orbit, sending it on a long, slow death spiral. As Planet V wandered, its gravity would have acted like a cosmic shepherd, but one herding its flock toward disaster. It perturbed countless asteroids in the inner belt, nudging them onto new, dangerous paths that sent them careening toward the inner planets. This would explain the sudden and intense barrage that scarred so many worlds. The existence of Planet V offered a neat, elegant solution to a long-standing mystery, a single culprit for a system-wide catastrophe. Yet many scientists today find the theory less compelling. Newer, more sophisticated computer models suggest the late heavy bombardment's fingerprints can be explained by the natural migration of the giant planets alone, without requiring a fifth terrestrial world to act as a trigger. The very instability that might have doomed Planet V could have scattered asteroids directly, making the lost planet an unnecessary complication. So, Planet V remains a ghost, a beautiful and logical idea that may ultimately be a scientific redundancy. Its story highlights a crucial process in our quest to understand lost worlds. We propose them to solve a puzzle, and sometimes their greatest value is in forcing us to find a better, simpler answer. The Ghost of Planet V challenges us to ask, did we lose a world? Or did we simply imagine a character to play a role in a cosmic drama that was already complete without it? While the Ghost of Planet V remains a scientific question mark, another lost world left a legacy that is literally written in the sky above us every single night. This is the story of Theia, a Mars-sized protoplanet whose catastrophic demise did not just create debris, it forged the Moon. The leading explanation for our lunar companion's origin is the giant impact hypothesis, a scenario of almost unimaginable violence. Picture the early solar system, a chaotic construction site where dozens of embryonic planets were vying for position. In this orbital dance, the path of a young, still molten Earth intersected with that of Theia. The collision was not a glancing blow. It was a direct, world-shattering impact that fused the two bodies together in a blaze of incandescent rock and vaporized metal. The energy released was so profound that it likely melted the entire Earth into a global magma ocean, while a colossal plume of material, a mixture of Theia's mantle and our own, was blasted into orbit. In the cooling calm that followed this cosmic forge, that ring of debris rapidly coalesced under its own gravity, giving birth to our moon. This is a loss of a different kind. Theia did not simply vanish into the void or shatter into anonymous fragments. Its substance was absorbed, its identity erased in the most creative act of destruction imaginable. The evidence for this epic event is not just in computer models, it is locked within the moon itself. When Apollo astronauts brought back samples of lunar rock, scientists made a startling discovery. The moon is surprisingly poor in heavy, dense metals like iron when compared to Earth. This makes perfect sense if the moon formed primarily from the rocky mantles of both worlds, while the dense metallic cores of Earth and Theia sank and merged into our planet's large inner core. Furthermore, the oxygen isotopes in lunar rocks are virtually identical to those on Earth. Isotopes are different forms of the same element, and they act as a planetary fingerprint. This isotopic twinship suggests the two colliding bodies formed in the same general region of the solar system, their raw material drawn from the same cosmic reservoir. Theia did not just hit us, it was our neighbor. The search for Theia continues, not by looking for its ghost in the darkness, but by looking for its chemical ghost within our own world. Some scientists are now exploring a fascinating possibility. Deep within Earth's mantle, seismic scans have revealed two colossal, mysterious blobs of dense rock, each the size of a continent. One lies beneath Africa, the other beneath the Pacific Ocean. Could these be the final, unmelted remnants of Theia's iron-rich mantle, sinking to rest just above our core? It is a tantalizing idea that the corpse of the world that created our moon might still be entombed within the Earth we walk upon. Theia's story is the ultimate paradox of a lost planet. Its existence was erased in a single, fiery moment, yet that very act of destruction gave us the celestial companion that stabilizes our planet's tilt, creates our tides, and has guided humanity for millennia. We look up at the moon and we are looking at the beautiful, reborn ghost of a world we never knew. our solar system's story of loss does not end with the giants. Far beyond the orbit of Neptune, in the deep freeze of the Kuiper belt, the hunt for phantom worlds continues. This vast, disc-shaped region is home to countless icy bodies, the frozen leftovers from the solar system's birth. Yet their strange, clustered orbits tell a story of gravitational disturbance, hinting at the presence of something massive we cannot yet see. This search began long before we knew the Kuiper belt existed. In the early 20th century, astronomers Percival Lowell and William Pickering were convinced that the wobbles in the orbits of Uranus and Neptune could only be explained by a ninth planet, a colossal world they called Planet X. Their calculations sent telescopes searching for this hidden giant. The search culminated in 1930 when a young astronomer named Clyde Tombaugh, working at Lowell's own observatory, found a faint, moving point of light. He had discovered Pluto. For decades, Pluto was celebrated as the ninth planet, the triumphant discovery of Planet X. But over time, doubts grew. Pluto was shockingly small, far too tiny to exert the gravitational pull needed to perturb the gas giants. The original wobbles were chalked up to observational error, and Pluto's status as Planet X was revoked. Then, in the 1990s, astronomers began discovering other small, icy worlds in Pluto's neighborhood. They realized Pluto was not unique, but simply the largest known member of a vast population. This led to its controversial reclassification as a dwarf planet in 2006. Pluto's journey from a predicted giant to a reclassified dwarf is a modern echo of Vulcan's story. It was a world found because we were looking for a ghost, only to discover a reality far more complex and interesting. The search for Planet X, however, has evolved, not ended. Astronomers studying the Kuiper belt have noticed a bizarre pattern. The most distant objects, those with incredibly long, elliptical orbits, are not scattered randomly. Their orbits are clustered together, as if shepherded by an unseen force. The most compelling explanation for this gravitational signature is a hypothetical object known as Planet 9. This would not be a small, rocky world, but a true giant, a super-Earth or a mini-Neptune with a mass up to 10 times that of our own planet. Its proposed orbit is immense, taking perhaps 20,000 years to complete a single journey around the Sun. Finding it is a monumental challenge, like searching for a single, dim star in the entirety of the night sky. The evidence for Planet 9 is indirect, written in the aligned paths of these distant icy bodies. Its existence would solve the orbital mystery, but its non-existence would be even more profound, forcing us to find a new explanation for why these frozen worlds dance in such perfect, unexpected harmony. The outer solar system remains the final frontier for lost planets, a place where our maps are still blank and the ghosts of worlds yet to be found, or yet to be disproven, beckon from the darkness. The idea of a dark twin to our Sun is one of the most chilling hypotheses in modern astronomy. The Nemesis star theory suggests our solar system is not a single star with planets, but a binary system with a faint, distant companion. This object, likely a dim red dwarf or a failed star known as a brown dwarf, would orbit our Sun on an immensely long path, taking tens of millions of years to complete a single cycle. Its gravitational influence would be minimal for most of that time, until its orbit brings it swinging through the outer Oort cloud, that vast, spherical shell of icy bodies at the very edge of the Sun's influence. As this dark star plows through this reservoir of frozen comets, its gravity acts like a gravitational paddle, stirring up the primordial ice and sending a deadly shower of comets hurtling inward toward the planets. The implications for Earth are terrifyingly cyclical. This theory was proposed to explain a grim pattern in our planet's fossil record. the apparent regularity of mass extinction events. The most famous of these, the extinction of the dinosaurs 66 million years ago, was likely caused by a massive asteroid or comet impact. If Nemesis were real, its periodic visits would be a celestial clock, ticking off eras of life and death on our world. For a time, this dark star was a serious scientific candidate, a ghost whose fingerprints were seen in the craters of Earth and the rhythmic dying of species. The search for Nemesis consumed considerable effort. Astronomers scanned the skies for any hint of this dim, slow-moving object, but every survey came up empty. As our maps of the solar neighborhood became more complete, the possible hiding places for such a star shrank to nothing. The statistical evidence for periodic extinctions itself was called into question, with many paleontologists arguing the pattern was not as regular as it first appeared. The cosmic clock, it seemed, was broken. Nemesis has largely been relegated to the realm of compelling but unproven ideas. Yet its legacy endures. It represents a profound shift in how we see our place in the cosmos, forcing us to consider that the greatest threats to life on Earth may not come from within, but from the gravitational machinations of a phantom we cannot see. It is a reminder that our solar system's history may be written not just in the planets we have, but in the unseen dancers that may still lurk in the perpetual night. The story of cosmic loss does not end with planets. Entire moons, the faithful companions of worlds, can also vanish into the void. Consider our own familiar moon, a constant in our sky. But what if Earth once had a second, smaller companion? In the late 19th century, the respected astronomer Frédéric Petit claimed to have observed just that, a tiny second moon of Earth. He calculated its orbit and even gave it a name, Lilith. Other astronomers searched for this phantom satellite, but no one could ever confirm its existence. It was likely a case of misidentified asteroids or observational error, but for a brief moment, the idea of a second moon captured the imagination, a ghostly twin to our own lunar companion. This story of Lilith reminds us that our own cosmic neighborhood might have once been more crowded, its history written in celestial absences we can no longer see. The forces that can steal away a moon are immense. Look at the scorched, airless worlds of Mercury and Venus. Their barren landscapes suggest a history of extreme violence. Some planetary scientists have proposed that these inner worlds might have once possessed their own small moons, captured asteroids from the chaotic early solar system. But orbiting so close to the Sun's gravitational grasp would have been a precarious existence. The Sun's powerful tides would have acted like a constant, relentless drag, slowly sapping the orbital energy of any small satellite. Over millions of years, these hypothetical moons would have spiraled inward, eventually crossing the Roche limit, the point where a planet's gravity overwhelms the moon's own structural integrity. They would have been torn apart, their debris raining down onto the planet's surface or being vaporized by the intense solar heat. Alternatively, a catastrophic collision with another large body could have simply blasted a moon away entirely, sending it hurtling into the Sun or out into the lonely depths of space. The silence around Mercury and Venus, their lack of lunar companions, might be the final evidence of this ancient theft. These stories of lost moons expand our definition of cosmic loss. It is not always about the destruction of a primary world. Sometimes it is about the severing of a gravitational bond, the dissolution of a partnership that may have lasted for eons. A planet without its moon is a different world, its rotation, its climate, its very stability altered by the absence. If Earth had lost its moon in the distant past, our planet would be a far more chaotic place, with a wobbly axis causing wild climatic shifts. The loss of a moon is a quieter, more subtle kind of ghost story. one where the evidence is not in what remains, but in the profound silence and solitude left behind. What other lonely worlds, stripped of their companions, drift through the galaxy, their past partnerships erased by time and gravity? But the chaos of the early solar system may not have been an isolated event. Our entire galaxy is a swirling sea of stars, and sometimes the tides of that sea can cast entire worlds adrift. These are rogue planets, dark nomads ejected from their own star systems and condemned to wander the infinite cold between the stars. Our Sun, in its long journey around the galactic center, could have sailed right through a cloud of these lost worlds. The gravitational pull of our star and its giant planets might have briefly captured one, pulling a wandering ice giant into a temporary orbit. Imagine the scene: a frozen colossus, dark and silent after eons in the void, suddenly snared by the sun's gravity. It would have swept into the outer solar system on a long, elliptical path, a ghost at the feast of established planets. Its presence, even for a few thousand years, would have been profoundly disruptive. A massive interloper weaving through the orbits of Neptune and Uranus would have acted like a bull in a cosmic china shop. Its gravity would have given these giants a sharp pull, altering their paths and potentially scattering the smaller icy bodies in the Kuiper belt into the strange, clustered orbits we see today. Then, just as suddenly as it arrived, the complex gravitational dance of the solar system would have flung it back out into the darkness, a temporary captive returning to its eternal exile. The entire episode might have been a mere blink in cosmic time, but its ghostly signature could be frozen into the orbital patterns we observe billions of years later. This idea transforms our solar system from a closed family into a dynamic port, where celestial visitors can come and go, leaving their mark on history before vanishing without a trace. How many other wandering worlds have brushed past our sun, their brief passages leaving clues we are only now learning to read? Our search for lost worlds now leaps beyond our solar system to a star 25 light-years away. Around the bright star Fomalhaut, astronomers spotted a tiny, brilliant pinprick of light, a world they named Fomalhaut b. It was a landmark discovery, one of the very first exoplanets ever directly seen, not just inferred from the wobble of its star. For years it was celebrated, a jewel in the crown of the new science of exoplanet hunting. But then, something impossible happened. The planet began to fade. Subsequent observations with the Hubble Space Telescope revealed this was no stable world. The point of light was not holding its orbit. Instead, it was expanding and growing dimmer, like a puff of smoke dissipating in a gentle breeze. The brilliant discovery was literally vanishing before the eyes of the scientific community. So what was it, if not a planet? The most compelling explanation is one of catastrophic violence. Fomalhaut b was likely never a full-fledged planet at all. Astronomers now believe we witnessed the aftermath of a collision of almost unimaginable scale. Two large, icy protoplanets, each perhaps hundreds of miles across, slammed into one another right as we were watching. What Hubble captured was not a planet, but the incandescent, expanding cloud of vaporized rock and pulverized ice from that impact, a cosmic firework that glowed for a few brief years before fading into the darkness from which it came. This case is a profound lesson in humility. It underscores the immense difficulty of directly imaging planets around other stars. We are looking across trillions of miles of space, trying to discern a faint speck of light next to the overwhelming glare of its sun. It is all too easy for that speck to be something else entirely, a dust cloud, a background star, or the ghost of a world that died just as we found it. Fomalhaut b reminds us that the universe is not a static museum. It is a dynamic, often violent arena where creation and destruction happen in real time. Our telescopes are not just mapping a stable cosmos, they are catching glimpses of an endless, unfolding drama. What other celestial phantoms have we mistaken for permanent worlds, and how many more are dissolving into dust even as we search for them? The most compelling evidence for a lost world is often the hole it leaves behind. Astronomers hunt for these phantom planets not by training their telescopes on empty space, but by reading the subtle disturbances they imprint on the cosmos. The first and most powerful tool is the analysis of gravitational perturbations. Just as you might sense a person's presence in a dark room by a faint draft or a shift in the shadows, scientists detect unseen worlds by watching how known objects behave. A star might wobble in a way that suggests an orbiting planet is tugging on it. The orbit of Neptune might show a tiny, unexpected kink, a gravitational signature pointing toward a massive, hidden body farther out. These are not giant, obvious effects. They are whispers in the data, minute deviations that require incredibly precise measurements to detect. For decades, this was the primary method for planet hunting, and it is how the search for Planet 9 continues today. Scientists meticulously track the paths of distant Kuiper belt objects, looking for that shared, telltale alignment that hints at a giant shepherd hiding in the dark. Another critical technique involves studying cosmic crime scenes, the vast disks of dust and debris that surround young stars. These are not placid, uniform rings. They are dynamic environments, and their structure tells a vivid story. A sharp gap in a debris disk might be cleared out by the gravity of a newly formed planet, like a snowplow pushing aside a path. A bright, concentrated clump of dust could be the aftermath of a recent, catastrophic collision between two protoplanets, the glowing cloud of their shattered remains. By analyzing the composition and distribution of this dust with powerful instruments like the ALMA telescope array, astronomers can work backwards. They can determine the size of the objects that collided, the violence of the impact, and even estimate when it happened. We are essentially studying the smoke to understand the fire, reading the scattered evidence to reconstruct a planetary disappearance that might have occurred millions of years ago. Finally, there are the digital time machines, the complex N-body simulations that model the gravitational dance of the solar system. The term N-body simply refers to the number of objects in the simulation, whether it is 4 planets or 400. Scientists program these virtual universes with the known laws of physics and set them in motion, running the clock backwards and forwards over billions of years. They can test the Planet V hypothesis by adding a fifth rocky world to the early inner solar system and watching what happens. Does its gravitational influence trigger a late heavy bombardment? They can test the fifth giant theory by simulating a young Jupiter interacting with a sibling ice giant. Does the model consistently eject one of them, leaving behind the orbital arrangement we see today? When the outcome of these digital experiments matches the reality we observe, it provides powerful, though indirect, support for the existence of a lost world. This toolkit of perturbations, debris forensics, and computer modeling represents a fundamental shift in how we do science. We are no longer just cataloging what we can see. We are becoming cosmic historians, piecing together the entire story of our solar system from the ghostly fingerprints left in the void. These collisions are not gentle nudges. They are the ultimate cosmic erasers, capable of wiping a world from the ledger of existence in a single, fiery instant. The physics of such an event is governed by two brutal forces, gravity and momentum. When two planetary bodies meet, the outcome hinges on their speed, their angle, and their sheer mass. A glancing blow might be enough to radically alter a planet's orbit, sending it spiraling into its star or flying out into the void. But a direct head-on impact is a different kind of apocalypse. The energy released is beyond human comprehension. For a moment, both worlds cease to be solid. They become an incandescent fluid, a superheated plasma of rock and metal. The shockwave propagates through both bodies, shattering them from the inside out. If the impactor is large enough and fast enough, it can completely disrupt the planet's gravitational binding energy, the fundamental force that holds the world together. When that happens, the planet doesn't just break apart. It explodes, its fragments scattered into a new asteroid belt or a cloud of dust that will eventually disperse. We can see the echoes of these violent processes all across our own solar system. The surface of Mercury is a single, sprawling crater, a testament to a bombardment so severe it left no ancient plain untouched. The stark dichotomy of Mars, with its smooth northern lowlands and cratered southern highlands, hints at a colossal impact that may have scraped away half of the planet's crust. Our own moon's birth from the collision with Theia is the ultimate example of creative destruction. Computer simulations allow us to replay these cosmic catastrophes in slow motion. Scientists input the mass, velocity, and composition of two colliding bodies and let the laws of physics take over. The results are both beautiful and terrifying. We can watch as a Mars-sized object plunges into a young Earth, see the mantle of both worlds splashed into orbit, and witness the rapid assembly of that debris into a new moon. Other simulations show a smaller, faster impactor punching straight through a planet's core, leaving it a shattered, molten wreck. These digital experiments reveal a crucial truth. A planet's death is not always a quiet fading. More often, it is a spectacular, violent event that reshapes entire solar systems. The craters we see are not just scars, they are the graves of worlds that never were, and the birth certificates of the worlds we know. What silent, cratered surfaces on distant moons hold the final evidence of a planet that was utterly erased? A world can be torn from its star without a single collision. This silent, bloodless ejection relies solely on the relentless pull of gravity. In a young, crowded planetary system, massive worlds orbit in a delicate balance, their paths constantly tweaked by each other's influence. It is a cosmic dance, but one that can turn deadly. When two planets draw too close, their gravitational fields interact in a complex slingshot maneuver. One world, usually the lighter of the two, can gain a tremendous burst of orbital energy. It is flung outward at a speed that can exceed the star's gravitational escape velocity, breaking the bond that tethered it to its stellar parent forever. This is not a gentle push into a wider orbit. It is a permanent exile into the interstellar void. The recoil from this event is just as significant. The planet that did the flinging, often a gas giant like Jupiter, will typically lose energy and settle into a tighter, warmer orbit closer to the star. This single process of gravitational scattering can therefore explain two puzzling features at once: the absence of a world and the unexpected placement of another. The galaxy is likely teeming with the results of this cosmic chaos. Billions of rogue planets, frozen and dark, may now drift between the stars. These are not worlds that formed in isolation. They are the lost children of solar systems, cast out during the violent gravitational sorting of their youth. Their surfaces, if they have any, are frozen wastelands, their internal heat the only remnant of the stellar warmth they once knew. To stand on such a world would be to experience the ultimate solitude beneath a sky of unbroken black, the parent sun having faded to a distant, indistinguishable pinprick among millions. This process solves a practical mystery for astronomers. Our models of planet formation often produce systems that are too crowded and unstable to survive. Gravitational ejection is the universe's way of taking out the trash, removing excess worlds to create the stable, well-ordered systems we observe today. The quiet, mature solar system we inhabit is a peaceful neighborhood precisely because its violent past expelled the troublemakers. Our own solar system's possible fifth giant is a prime candidate for this fate, a ghost whose departure brought our current stability. How many other stars, then, have similar ghosts in their past, worlds that were sacrificed to the darkness so that order could emerge from the chaos? A star's death is a celestial apocalypse for any worlds that orbit too close. When a star like our Sun exhausts its nuclear fuel, it does not go quietly. It swells into a monstrous red giant, its outer layers expanding to engulf the inner planets. Mercury, Venus, and likely Earth itself would be vaporized, their substance simply absorbed back into the star's fiery atmosphere. But this is only the beginning of the end for a planetary system. After the red giant phase, the star's core collapses, leaving behind an incredibly dense stellar remnant. This is where the true gravitational tyranny begins. The most common relic is a white dwarf, a Earth-sized cinder packing the mass of a star. Its gravity is so intense that any surviving or newly wandering planet that ventures too near will be torn apart. The star's gravitational pull on the near side of the planet becomes vastly stronger than the pull on the far side. This difference, the tidal force, stretches the world like taffy, overcoming the gravity that holds it together. The planet is shredded into a swirling ring of asteroidal rubble, a disk of debris that slowly rains down onto the white dwarf's surface. Astronomers have actually observed this, finding the spectral signatures of pulverized rock and metal polluting the otherwise pure hydrogen and helium atmospheres of these dead stars. They are literally seeing the dust of obliterated worlds falling onto a stellar corpse. The fate near a neutron star is even more extreme. A neutron star is a city-sized object with the mass of 1.4 suns, a density so absurd that a teaspoon of its material would weigh billions of tons. Its gravitational and magnetic fields are unimaginably powerful. A planet straying into its vicinity would not just be tidally disrupted, it would be vaporized by intense radiation and shredded into a cloud of subatomic particles, its very atoms torn asunder. And then there is the black hole, the ultimate cosmic destroyer. Within its event horizon, the point of no return, the tidal forces become infinite. The concept of a solid object ceases to have any meaning. A planet crossing that threshold would be spaghettified, stretched into a long, thin stream of elementary particles before being added to the singularity's mass. Its information, its history, its very identity would be erased from the universe. This is the most final form of disappearance, a loss so complete that not even light can escape to testify that the world was ever there. The death of a star does not just mean the lights go out. It means the demolition of entire worlds, a final, violent rewriting of a solar system story where the planets themselves become mere footnotes in the obituary of their sun. Gravity can also build prisons of exquisite precision. Far from the chaotic scattering of rogue planets, some worlds become locked in a delicate gravitational dance known as an orbital resonance. This is not a random tug of war, but a rhythmic, repeating pattern. Imagine two moons orbiting a planet. For every single orbit the inner moon completes, the outer one completes exactly two. Their gravitational pulls reinforce each other at the same points in their paths, creating a stable, predictable rhythm that can last for billions of years. We see this harmony in our own solar system. 3 of Jupiter's largest moons, Io, Europa, and Ganymede, are locked in a perfect 1-2-4 resonance. Io orbits 4 times for every 2 orbits of Europa and every single orbit of Ganymede. This constant, gentle nudging keeps their orbits circular and stable, preventing them from ever drifting too close and colliding. It is a celestial waltz choreographed by gravity that protects these worlds from each other. But this same force has a dark and destructive twin. A resonance can also act like a relentless metronome, ticking off beats of instability. If a planet's orbit brings it into a destructive resonance with a much larger world, the effect is catastrophic. Each time the smaller planet passes the giant, it receives a tiny, identical gravitational kick. These kicks do not cancel out. Instead, they build up over millions of years, like a child on a swing being pushed at exactly the right moment to go higher and higher. The planet's orbit becomes more and more elongated, more elliptical, until it crosses the path of another world or is flung entirely out of the system. This is how a resonance can become a death sentence, a slow, inexorable guide toward oblivion. The difference between preservation and destruction lies in the specific numbers of the dance and the masses of the partners involved. A gentle rhythm between siblings can create eternal stability, while the same rhythm imposed by a giant can lead to a fatal crescendo. Our own solar system's asteroid belt is scarred with gaps, empty lanes where no asteroid can maintain a stable orbit. These are the Kirkwood gaps, and they exist at precise distances from the Sun where an asteroid would orbit in a simple resonant ratio with Jupiter, like 2:1 or 3:1. Any asteroid that wanders into these zones is quickly ejected by Jupiter's periodic, amplified tugs. It is a clear, lasting imprint of resonance as a destructive force, a ghostly fence built not of rock but of pure gravity. So, which factor decides the fate of a world caught in this dance? Is it the mathematical purity of the ratio or the sheer power of the gravitational partner? The answer seems to be a fragile combination of both, a cosmic balance that can tip from harmony to chaos with the slightest nudge. What other lost worlds were slowly, rhythmically marched to their end by a gravitational tyrant they never even touched? Gravity and collisions are tangible forces, but what if a planet's vanishing act defied these familiar rules entirely? Theoretical physics dares to ask this question, venturing into realms where the very fabric of reality might hold stranger possibilities for loss. Imagine the laws that govern our universe are not the only laws that exist. Concepts like string theory propose that the fundamental building blocks of everything are not particles, but incredibly tiny, vibrating strings. For these strings to have the properties we observe, the theory requires more than the 3 spatial dimensions we experience. It suggests the existence of extra dimensions curled up so small that we are utterly unaware of them. This is where the idea of brains comes in, a shorthand for membranes. Our entire universe, with all its stars and planets, could be a 3-dimensional brain floating within a higher dimensional space, like a single page in a colossal, multidimensional book. Now consider a cosmic event of unimaginable energy, perhaps a collision with a primordial black hole or a fluctuation in the underlying spacetime foam. Such an event could, in theory, cause a localized rupture or a shift. A planet might not be shattered or ejected, but simply nudged off our brain and onto another, parallel one. From our perspective, the world would have vanished without a trace, without debris or a gravitational echo. It would be gone, not to nowhere, but to somewhere else entirely, a somewhere we cannot access or even perceive. This is, of course, a highly speculative idea, far from any empirical proof. Yet, it fundamentally reframes the concept of a lost planet. It challenges our definition of existence itself. Is a world that has shifted to another dimensional plane truly destroyed, or is it merely lost to us? These are not questions astronomy can answer with a telescope, but they expand the horizon of our imagination. They push us to consider that the cosmos might be far more layered and mysterious than a simple collection of matter and energy. the ghost of a planet could be more than a memory or a mathematical error. It could be a resident of a reality forever adjacent to our own, separated by a veil thinner than an atom but more absolute than the deepest space. Every story of a lost world is also a story of life that might have been. The cosmic disappearances we have explored are not just celestial curiosities. They are events that directly shape the potential for biology across the galaxy. This brings us to the concept of the habitable zone, that narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface. It is often called the Goldilocks zone, not too hot and not too cold. A planet orbiting comfortably within this zone is a prime candidate for life as we understand it. But what happens when that stability is stolen? Consider a world like the hypothetical fifth giant, ejected from our solar system in its youth. If that frozen giant had once possessed a warm, watery moon, a place like Jupiter's Europa but orbiting within the habitable zone, its sudden catapult into interstellar space would have been an unimaginable catastrophe. The star's warmth would vanish, leaving the moon's oceans to freeze solid in a geological instant. Any fledgling life in those waters would be snuffed out, its world transformed into a permanent ice tomb drifting between the stars. This is cosmic sterilization on the grandest scale, the quiet death of a biosphere not by fire but by an eternal, deepening cold. Yet the same violent processes can also be creators. The cataclysm that formed our moon from Theia's impact was an event of pure destruction, but it also set the stage for life on Earth. The moon's gravitational pull stabilizes our planet's axial tilt, preventing wild climate swings that would make complex life difficult to evolve. Furthermore, the colossal energy of the impact remade Earth's entire surface, potentially creating the conditions for our planet's magnetic field and plate tectonics, both crucial for maintaining a stable environment over billions of years. Even the rubble of destruction can sow the seeds of life. When two protoplanets collide, as we saw with Fomalhaut b, the resulting debris cloud is rich in water ice, organic compounds, and minerals. This material can be scattered across a solar system, a phenomenon known as panspermia. A comet or asteroid carrying these building blocks could be flung inward by a gravitational slingshot, eventually crashing into a young, sterile world in the habitable zone. That impact, while violent, could deliver the very water and complex molecules necessary for life to begin. So, the destruction of one world might literally fertilize another. The asteroid belt itself, that graveyard of failed planets, may have been the source of the water in Earth's oceans, delivered by a rain of comets and asteroids during the late heavy bombardment. The fate of life in the universe is therefore tied to a delicate balance. A planet must be in the right place, but it must also have the right history, one that may include both the creative and destructive legacies of lost worlds. The ghost of a shattered planet might be the very reason a neighboring world teems with life, while the ghost of an ejected giant might represent a biology that never was. How many frozen, lifeless worlds drift in the darkness that were once, for a brief cosmic moment, perfect cradles for life? These celestial ghosts have long escaped the bounds of astronomy to haunt our collective imagination. The idea of a vanished world is a powerful archetype, a blank canvas upon which we project our deepest fears and questions. In literature, this theme finds its most chilling expression in the works of H.P. Lovecraft. His cosmic horror is built upon the bones of lost and forgotten worlds, ancient civilizations that reached staggering heights only to be wiped away by indifferent, godlike entities. For Lovecraft, a lost planet was not just a scientific curiosity. It was a testament to humanity's terrifying insignificance in a universe that does not care if we exist. His fictional Yith, a race that transplanted its consciousness across time to escape a dying world, embodies our dread of cosmic instability and the desperate lengths life might go to in order to survive an ultimate end. This is more than just fiction. It is a philosophical argument written in the language of stars and silence. Modern science fiction continues this tradition, but often with a more urgent human focus. Stories of rogue planets carrying the last survivors of a dead civilization explore themes of exile and resilience. Narratives about finding the artifacts of a long-vanished alien race ask profound questions about legacy and the impermanence of all achievement. Whether it is the destroyed planet Alderaan in Star Wars, a single event of horrific violence, or the slowly dying Earth in so many climate fiction novels, these stories are always about us. They force us to confront the fragility of our own existence. Our civilization, our history, even our biosphere could all be rendered into just another layer of cosmic dust, a footnote in a galactic history we will never write. This is the philosophical weight of a lost planet. It challenges the very human need for permanence. We build cities, nations, and monuments hoping they will last, yet the cosmos demonstrates that even worlds are not forever. The ghost of Vulcan and the myth of Phaeton are not merely errors or stories. They are ancient, recurring echoes of a truth we are only now beginning to scientifically grasp. Our solar system is not a fixed, eternal clockwork. It is a dynamic and sometimes violent system, and our place within it is the result of both creative and destructive forces that are utterly beyond our control. To gaze at the night sky is to look upon a graveyard of possibilities, a reminder that stability is a temporary gift, not a guaranteed state. What does our own future hold in a universe that so casually creates and unmakes entire worlds? Science is a story written in pencil, not ink, and sometimes its most compelling chapters are the ones we have to erase. The search for lost planets is littered with these cautionary tales, where human error and excitement conspired to create worlds that never were. One of the most persistent of these phantoms was born from a simple, understandable mistake. For centuries, astronomers using early telescopes reported seeing a small, dark moon orbiting Venus. They called it Neith after an Egyptian goddess. The sightings were made by reputable observers and the descriptions were consistent. Yet, no matter how hard others looked, Neith could not be reliably found. The most likely explanation is a series of optical illusions. Venus is an exceptionally bright object, and when viewed through the primitive lenses of the 17th and 18th centuries, internal reflections within the telescope itself could easily create a faint secondary image. The human brain, eager to find patterns, would then interpret this ghostly duplicate as a satellite. Once the idea was planted, confirmation bias took over, with each new sighting feeling like proof, until better instruments revealed the heartbreaking truth. The moon of Venus was a reflection of a reflection, a ghost in the machine of both telescope and mind. Then there are the deliberate deceptions, the hoaxes crafted to fool the world. In the late 1800s, a French astronomer named L. Trouvelot announced he had observed a swarm of small, black bodies transiting the sun. He called them the Vulcanoids, believing them to be a family of asteroids inside Mercury's orbit, the shattered remains of the lost planet Vulcan. While Trouvelot was likely sincere, his observations were never replicated. But the story took a stranger turn when, decades later, a sensationalist newspaper article claimed that a mysterious second moon of Earth had been discovered, causing widespread panic. This was pure fabrication designed to sell papers, yet it tapped into the same deep-seated fascination with hidden worlds that drove legitimate science. These stories of misinterpretation and fraud are not just footnotes. They are vital reminders of the scientific method's most crucial safeguard: independent verification. A single observation, no matter how compelling, is just a story. It only becomes a fact when others can follow the same map and arrive at the same destination. The Phantom of Neith and the hoax of the second moon teach us that the desire to discover can sometimes be our greatest obstacle to seeing what is truly there. They force a humbling question: how many of the celestial phantoms we chase are merely reflections of our own hopes, staring back at us from the infinite dark? Our modern hunt for these celestial ghosts has entered a revolutionary new era. The search no longer relies on fleeting glimpses or mathematical guesswork alone. Today, a new generation of space telescopes and ground-based observatories acts as our cosmic detectives, armed with tools of almost magical precision. They are sifting through the light of distant stars, searching for the faintest whispers of worlds that might be there, or confirming the profound silence where we once believed one existed. At the forefront is the James Webb Space Telescope, or JWST. This orbiting observatory is not just a more powerful eye, it is an entirely new kind of instrument. Its primary gift is infrared vision, allowing it to peer through cosmic dust clouds that block visible light. More importantly, it can dissect the light from a distant star with a spectrograph, breaking it into a detailed rainbow or spectrum. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere, if it has one. JWST can read that filtered light like a chemical barcode, identifying the specific gases present. It can search for the atmospheric signature of a hypothesized gas giant, or, one day, even the biosignatures of a living world. This is not just about finding planets, it is about studying the ghosts of their atmospheres, learning what they were made of just before they vanished. While JWST looks deep at individual systems, the Gaia spacecraft is conducting a monumental census of our entire galactic neighborhood. Its mission is astrometry, the precise measurement of the positions and motions of stars. Gaia is not looking for planets directly. Instead, it is watching for the telltale stellar wobble, that subtle dance of a star being gently tugged by an unseen orbiting world. But Gaia's data is so exquisitely precise that it can detect wobbles smaller than ever before, revealing not just planets, but their gravitational influence with stunning clarity. This data can either pinpoint the location of a hidden world like the hypothetical planet 9 by revealing its pull on the orbits of distant Kuiper belt objects, or it can definitively rule one out by showing that the observed stellar motions have another, simpler explanation. Back on the ground, observatories like the Keck in Hawaii or the VLT in Chile use a technique called radial velocity with incredible sensitivity. They measure the subtle color shifts in a star's light as it moves ever so slightly toward us and away from us, pulled by the gravity of an orbiting planet. Modern instruments can detect velocity changes as small as a slow walking pace, allowing them to find smaller, Earth-sized worlds that would have been completely invisible to astronomers just a generation ago. These tools are not working in isolation. They form a collaborative network, a single distributed instrument of discovery. A ground-based telescope might identify a star with a curious wobble. Gaia can then precisely map that star's path through the galaxy. Finally, JWST can turn its powerful gaze to that system, attempting to directly image any planets or analyze their atmospheres. This multi-pronged approach is transforming the search from a speculative hunt into a rigorous process of cosmic forensics. We are no longer just staring into the dark and hoping to see a ghost. We are now listening to the universe with such acute hearing that we can detect the faintest gravitational footsteps of a world that does not want to be found. What ancient cosmic disappearances will this new sensory power finally bring to light? Sometimes the most profound mysteries are not of worlds that vanished, but of a star that simply refuses to behave. KIC 8462852, better known as Tabby's star, presented astronomers with a puzzle unlike any other. Data from the Kepler Space Telescope revealed that this distant sun was dimming in impossible ways. It did not exhibit the clean, symmetrical dip of a planet passing in front of it. Instead, its light would plummet by staggering amounts, up to 22%, in erratic, jagged patterns. The dimming was both deep and irregular, as if something colossal and strangely shaped was moving in a chaotic dance around the star. The most exotic explanation captured the public's imagination, a theory proposing that we were witnessing the construction of an alien megastructure, a Dyson swarm designed to harvest stellar energy. This was a modern phantom, not a lost planet, but a world so technologically advanced that it was literally disappearing its own sun behind a veil of artificial constructs. For a moment, the ghost in the machine was not a failure of human observation, but a signal of intelligence beyond our own. The idea of a constructed world, a civilization building itself into a cosmic secret, was a powerful echo of our oldest myths about vanished advanced cultures. Yet science must always seek the simpler answer before embracing the extraordinary. Astronomers turned their most powerful tools toward the strange star, searching for the true nature of its shroud. The most plausible explanations proved to be natural, though no less fascinating. One leading theory suggested a massive, fragmented comet swarm, the icy remnants of a colossal collision, passing in front of the star in a disordered cloud. Another pointed to vast clouds of fine dust and debris, perhaps from the disintegration of a moon or a planet, creating a complex, patchy screen that occluded the starlight in those bizarre, unpredictable patterns. The key evidence came from follow-up observations, which showed that the star dimmed more in blue light than in red light. Small dust particles scatter blue light more effectively, which is exactly what was detected. A solid alien megastructure built from metal and rock would block all colors of light equally. The signature of dust pointed not to a technological ghost, but to a natural, if violent, cosmic process. Tabby's star did not reveal a lost world or an alien civilization, but it did something just as important. It became a celestial Rorschach test, reflecting our enduring hope that the cosmos holds more than just random chaos. It proved that a single point of anomalous light could reignite the age-old human fascination with cosmic disappearances, blurring the line between a scientific mystery and a story we desperately want to be true. What other stellar oddities are waiting in the data, their strange signals whispering of phenomena we have not yet even begun to dream of? These wandering worlds represent the ultimate form of cosmic exile. Rogue planets are celestial orphans, entirely untethered from the warmth and light of any star, drifting through the interstellar void in perpetual, frozen night. Their origins are almost always violent, born from the gravitational chaos of young solar systems. Many are ejected during the same planetary billiards game that may have cost our own solar system a fifth giant, flung away by the slingshot effect of a larger sibling's gravity. Others might form on their own, condensing directly from lonely clouds of gas and dust too small to ignite into a star. The sheer number of these dark wanderers is staggering. Some estimates suggest there could be billions, even trillions of them in our galaxy alone, outnumbering stars by a vast margin. To stand on the surface of such a world would be to experience the ultimate solitude. The landscape would be an eternal, airless deep freeze, lit only by the faint, unmoving gauze of the Milky Way. Your sun would not rise or set because there is no sun. The only warmth would come from the planet's own internal radioactive heart, a fading ember from its formation. Over billions of years, even this feeble heat would radiate away into the absolute cold of space. The world would gradually cool into a frozen cinder, its geology seizing up, its potential for any form of life extinguished forever. Yet this deep freeze is not necessarily the end of their story. The galaxy is a dynamic place, and these orphans are not always doomed to solitude. A rogue planet's journey through the darkness could bring it close to another star system. If it passes near a gas giant, it could be captured, pulled into a stable orbit to become a new, strange moon. More rarely, the star's gravity itself could snare the wanderer, adopting it as a new planet, albeit one on a distant, looping path. This means a rogue planet's exile could last for eons before it finds a new home, or it could be permanent. They are the ghosts of the galaxy, silent testaments to the instability of creation, forever moving through the shadows between the stars. What ancient, frozen histories are locked within these drifting worlds, and what could they tell us about the chaotic beginnings of countless lost solar systems? The dust surrounding a distant star can tell a story of creation or cataclysm. These glowing halos, known as debris disks, are far more than just raw material for building planets. They are also cosmic graveyards, the lingering evidence of worlds that met a violent end. When astronomers train their most powerful telescopes on these rings, they are not just looking at future worlds, but also at the ghosts of planets past. The key to reading these stories lies in the dust itself. The composition and structure of the disk act as a forensic report from a distant crime scene. A smooth, uniform ring of fine dust suggests a quiet, mature system where planet formation concluded long ago. But a very different picture emerges when we see clumps and asymmetries, bright arcs and strange concentrations of material. These chaotic features are the fingerprints of a recent and immense collision, an impact of such force that it could shatter a planet into trillions of pieces. The dust from such an event has a specific signature. It is warm, glowing brightly in infrared light because it is still close to the heat of the central star, a clear sign it has not had time to disperse. Its composition can be analyzed through spectroscopy, revealing a mix of vaporized rock and metal that could only come from the deep interior of a sizable world. We are essentially seeing the expanding cloud of debris from a planetary demolition, the final chapter of a world that no longer exists. This is not a slow fading, but a sudden, explosive erasure. The collision that created our own moon was one such event, though on a creative scale. In other systems, we see the aftermath of purely destructive crashes. The strange dimming of Tabby's star, for instance, is now widely believed to have been caused by a colossal cloud of dust, likely the pulverized remains of a moon or a planet. Every irregular debris disk is a potential monument to a lost world, a silent testament to the chaos that shapes every solar system. What appears as a serene ring of light around a star might actually be the glittering, expanding tomb of a planet we will never know. A world can remain physically intact yet become a ghost of its former self. This slow, insidious form of loss happens not through collision or ejection, but through the relentless breath of its own star. For planets orbiting too close to their suns, stellar volatility is a silent killer. The most dramatic events are solar flares, colossal explosions on a star's surface that release a tsunami of high-energy radiation across the electromagnetic spectrum. A single, powerful flare can deliver a planet-scorching burst of X-rays and ultraviolet light in a matter of minutes. But an even greater threat may be the coronal mass ejection, a billion-ton cloud of magnetized plasma hurled into space at millions of miles per hour. When this solar hurricane slams into a planet, it does not just create pretty auroras. It delivers a hammer blow to the world's atmosphere. The planet's magnetic field is its first and most vital line of defense, deflecting these charged particles like a shield. But if the planet is too small, too close to the star, or rotating too slowly, its magnetic field may be weak or non-existent. Without that protection, the incoming energy from a flare or ejection transfers its force directly to the atoms and molecules in the upper atmosphere. Think of it like a game of cosmic pool. The high-energy particles from the stars strike the atmospheric gases, giving them such a powerful kick that they achieve escape velocity. One by one, molecule by molecule, the planet's air is literally blasted away into the void. This is not a quick process, but over hundreds of millions of years, it can completely transform a world. A planet that began its life as a wet, temperate world with a thick atmosphere could be slowly cooked and stripped down to a barren, airless rock. Its oceans would boil away and be lost to space, its protective blanket torn from it by the very star that gives it light. We see potential evidence of this in our own solar system. Mars is a frozen desert today, but its surface is etched with river valleys and lake beds, clear signs it once had flowing water and a much denser atmosphere. What happened? Mars is a smaller world than Earth with a much weaker magnetic field. As the young sun went through a violent, flaring phase, it is likely that the Martian atmosphere was systematically eroded away, its water vapor broken apart by ultraviolet light, and its nitrogen and oxygen slowly swept away by the solar wind. The planet itself is still there, a monument in the sky, but its potential for life was irrevocably stolen. This is a different kind of lost world, one that did not vanish from the sky but had its soul stripped away, leaving behind a celestial corpse that haunts us with what might have been. How many Earth-like worlds in other solar systems have suffered this same fate, their atmospheres scoured away by the fury of an unstable star, leaving them as permanent, silent tombs? Far beyond the last known planets, in the absolute cold and dark, lies a spherical shell of icy remnants known as the Oort cloud. This is the solar system's final frontier, a vast reservoir of frozen planetesimals left over from our system's birth. But what if this deep freeze holds more than just cometary snowballs? Astronomers now ponder the existence of stealth planets, large, dark bodies with the mass of worlds, lurking unseen in this immense darkness. These would not be the predicted giants of old theories, but true phantoms, whose presence is betrayed only by the subtlest of clues. Their sole signature would be a faint gravitational whisper, a slight perturbation in the paths of long-period comets that occasionally swing in from the Oort cloud's depths. A comet's trajectory is a precise record of every gravitational nudge it has ever received. When a comet arrives on an orbit that cannot be explained by the known planets alone, it hints at a hidden puppeteer, a massive object whose gravity is subtly sculpting the paths of these icy wanderers. Finding such a stealth planet would be the ultimate cosmic detective story. It would be a world of profound darkness, reflecting virtually no light, and so distant that the sun would appear as little more than a particularly bright star. Its surface would be a frozen landscape of primordial ices, a time capsule from the solar system's very first moments. Is our solar system's Oort cloud a silent graveyard, or does it secretly host dark, wandering giants, the final and most elusive ghosts in our celestial attic? Our minds are wired to solve puzzles, to close the circle and complete the story. An unfinished mystery creates a deep, cognitive itch, a need to find the missing piece that will make the entire picture snap into focus. This is the powerful allure of a lost planet, a world that we know must have existed or that we once believed was real, represents a cosmic blank space, an invitation for our imagination to rush in and fill the void. We are not satisfied with a map that has a hole in it. we feel compelled to draw in the missing continent, even if we only have the faintest whispers of its coastline. This drive is more than simple curiosity. It is a fundamental part of how we understand our place in the universe. A known planet like Jupiter or Saturn is a fact. It is settled, but a phantom world like Vulcan or Planet 9 is a living question, a story still being written. The unknown is always more dramatically compelling than the known because it holds infinite possibility. It allows us to project our hopes for discovery, our fears of cosmic chaos, and our awe at the sheer scale of what we do not understand. Think of a detective faced with a locked room mystery. The known facts are the locked door and the empty room, but the unknown, the vanished occupant, is what fuels the entire investigation. Our fascination with lost worlds is the same. The empty space in a star's gravitational field, the strange alignment of icy rocks in the Kuiper belt, these are the locked rooms of the cosmos. We are the detectives, and we cannot rest until we have theorized every possible suspect and scenario. This psychological need for a complete narrative is why the idea of a shattered planet forming the asteroid belt is so enduring, even as the science grows more complex. It provides a clean, satisfying story, a single catastrophic event that explains a sprawling, messy reality. Our brains crave that kind of order. We prefer a dramatic, definitive ending, even a violent one, to the unsettling ambiguity of a process that was simply never finished. The ghost of a lost planet is a permanent question mark hanging in the sky, and for the human spirit, a question mark is an irresistible call to adventure. The ghostly worlds we have chased so far are echoes from the past, but one planet is vanishing before our very eyes. Orbiting a star 1,400 light-years away, the exoplanet WASP-12b is caught in a death spiral, offering us a front-row seat to a planetary apocalypse. This world is a hot Jupiter, a gas giant searingly close to its sun, completing an entire orbit in just 26 hours. Its proximity has turned it into a blistering inferno, with dayside temperatures soaring to over 4,000 degrees Fahrenheit. But the heat is not what is killing it. Gravity is the true executioner. The star's immense gravitational pull does not just keep the planet in orbit, it actively tears at its atmosphere. Because WASP-12b is so close, the difference in the star's gravitational pull between the planet's near side and its far side is staggering. This tidal force has stretched the entire world into an egg shape, and it is systematically ripping the atmospheric gases from its surface. A constant supersonic wind of hydrogen and helium streams from the planet, being siphoned directly into the star. This stolen material does not fall straight in, instead forming a scorching hot disk of gas that spirals around the star, a visible funeral shroud for the dying planet. Astronomers call this an accretion disk, and its presence confirms the world is being consumed bite by bite. Estimates suggest WASP-12b is losing a mass equivalent to 39 quintillion pounds every second, a rate that will lead to its complete destruction in about 10 million years. While that seems like an eternity to us, in cosmic terms it is a blink of an eye. This is a slow-motion version of the catastrophes that may have shattered other worlds, a drawn-out stellar meal we are privileged to witness. The planet is not lost yet, but its fate is sealed, a grim reminder that the universe is not a still life, but a dynamic arena of creation and destruction happening in real time. What other worlds are currently undergoing their own final act, their light slowly fading as they are pulled into the abyss? The violence of a dying planet is a local tragedy, but the true scale of loss encompasses the entire galaxy. Our Milky Way is not a serene island of stars, it is a product of brutal mergers and cosmic cannibalism. One of the most profound pieces of evidence for this is a structure astronomers call the Gaia sausage. This is not a stellar snack, but the ghost of a dwarf galaxy that collided with and was devoured by our own Milky Way some 8 to 10 billion years ago. Data from the Gaia Space Telescope revealed that a vast population of ancient stars, millions of them, are not moving in random orbits. Instead, they follow highly elongated radial paths, all plunging in and out of the galactic center on similar trajectories. When mapped, this motion forms a distinct sausage-like shape embedded within our galaxy's halo. These stars are the surviving population of that devoured galaxy, the celestial refugees of a galactic smash-up of unimaginable force. Their very motion is a fossil record of that ancient collision. Now consider the planetary systems that once orbited these stars. Before the merger, a dwarf galaxy would have contained billions of stars, many likely hosting their own families of planets. The gravitational turmoil of the merger would have been absolute chaos for these worlds. As the two galaxies intertwined, the delicate gravitational balances within each planetary system were violently overthrown. Stars that once drifted in peaceful isolation were suddenly flung past each other at close range. The gravitational pull from a passing star, even a small one, would have been enough to act as a cosmic cue ball, disrupting the orbits of planets light years away. Imagine a solar system much like our own, with planets orbiting in stable, circular paths. Then, a rogue star from the intruding galaxy passes within 1 trillion miles, a relatively close shave on the galactic scale. Its gravity would deliver a sharp, unexpected tug to every planet in that system. For the outer planets, this could be enough to fling them into the interstellar void. For the inner planets, it could push their orbits into crossing paths, triggering a cascade of catastrophic collisions that would shatter worlds into asteroidal dust. The Gaia sausage event was not a single moment, but a protracted period of galactic violence that may have lasted for billions of years. During this time, the number of planets lost to ejection or destruction must have been staggering. This single act of galactic cannibalism likely sterilized countless worlds that might have been cradles of life, their potential erased before it ever had a chance to begin. We are left with the silent testimony of the stars themselves, their strange orbits a permanent memorial to a lost planetary history written in fire and gravity. The quiet, stable galaxy we see today is built upon the ruins of a devoured sibling, and the ghosts of its planets are a fundamental part of our own cosmic heritage. The hunt for these celestial ghosts is accelerating with tools of unprecedented power. The next decade promises to either confirm the existence of phantom worlds or finally lay their legends to rest. A key player in this cosmic investigation is the Vera C. Rubin Observatory, currently under construction in Chile. Its mission is nothing less than a complete, dynamic movie of the southern sky. Night after night, its enormous camera will capture panoramic images, allowing scientists to track the motions of billions of objects. This relentless survey will map the outer solar system with a thoroughness we have never achieved before. It is designed to find the subtle, shepherding influence of a massive hidden planet by precisely tracking the orbits of distant icy bodies. If Planet 9 is out there, the observatory's data should reveal its gravitational signature etched into the paths of these frozen worlds. Alternatively, if no such pattern emerges, it could definitively close the book on one of astronomy's most tantalizing modern quests. Beyond this grand survey, our understanding of planetary disappearances is being reshaped in supercomputers. Theorists are building increasingly sophisticated models of the early solar system's chaotic dance. These are not simple animations. They are complex digital universes governed by the precise laws of physics. Scientists can run thousands of simulations, each with slightly different starting conditions, to see which scenarios most reliably produce the solar system we see today. Do the models consistently eject a fifth giant planet? Does the orbital evidence require a lost world like Planet V to trigger the late heavy bombardment, or can the giant planets alone explain the cratering? These virtual time machines are testing the limits of our cosmic history, providing statistical weight to what was once pure speculation. The future also lies in dissecting the light from other stars with even greater precision. The James Webb Space Telescope is just the beginning of a new era of atmospheric forensics. Future missions will analyze the chemical composition of debris disks around young stars, looking for the specific elemental signatures of recent planetary collisions. They will search for the faint thermal glow of rogue planets drifting in the dark between stars, estimating their numbers and understanding their origins. Every new piece of data, whether from a giant telescope on a mountain or a spacecraft orbiting 1,000,000 miles from Earth, is another clue in this grand investigation. We are no longer just telling stories about lost worlds. We are gathering the evidence to put them on trial. The verdict on our solar system's most enduring phantoms is closer than it has ever been. Will we find them, or will we discover that the universe's true mysteries are even stranger than the ghosts we invented? So many worlds have vanished in so many different ways. We have seen planets shattered in collisions, flung into the void by gravitational slingshots, or stripped of their atmospheres by stellar fury. Is there a single, unifying thread connecting these disparate acts of cosmic loss? Or are we simply witnessing the random, chaotic outcomes of a violent universe? Perhaps the true grand narrative is not a specific event, but a fundamental principle, the relentless drive of physical systems toward stability. In this framework, the disappearance of a world is not a tragedy, but a necessary step in the universe's quest for equilibrium. A young solar system is a chaotic construction site, filled with excess material and unstable orbits. The ejection of a fifth giant planet, the collision that formed our moon, even the grinding down of the asteroid belt by Jupiter's gravity, all these events can be seen as the system shedding its instability. The lost worlds are the sacrificial pieces in a cosmic game of gravitational chess, removed from the board so that the remaining planets can settle into the stable, resonant orbits we observe today. This principle operates on every scale. A star strips a planet's atmosphere to restore balance to its own energetic output. A galactic merger scatters entire planetary systems to create a new, more stable elliptical galaxy. Even the theoretical shift of a world into another dimension could be interpreted as the universe resolving a paradox or an impossible energy state. Yet, for every case that fits this neat narrative, there is an exception that revels in pure chaos. The bizarre, unpredictable dimming of Tabby's star points to a messy, one-off catastrophe, not a systematic cleansing. The sheer number of rogue planets suggests that ejection is not a rare, stabilizing event, but a common and almost careless byproduct of planetary formation. And what of the worlds that never were, like the stillborn planet in the asteroid belt? Their story is not one of loss, but of a creation that was never permitted to begin, a potential snuffed out by a gravitational tyrant before it could even draw its first breath. This leaves us with a humbling duality. We can see the elegant hand of stability shaping our cosmic neighborhood, clearing the chaos to create a haven where life could eventually emerge. But we are also forced to acknowledge the raw, untamed chaos that underpins it all, a universe that creates and destroys with an indifference that is both beautiful and terrifying. Our solar system's quiet maturity is not the rule, but the exception, a fleeting moment of calm purchased by the sacrifice of countless ghosts. As we prepare to draw our final conclusions, we must ask, Does this search for lost worlds ultimately tell us more about the cosmos, or about our own profound need to find order in the silence?